that the seniors who are on the senior frou-frou can hear us. And we're going to do two things today. The first thing that we're going to do is I'm going to go back over some of the material on logarithms and talk about 3 classic problems that you need to be able to do. And then if we have time, I'll talk a little bit about what I was going to talk about today, which is using the calculator to solve trig equations. So it's a busy day, and it all depends on how much time we've got. And here's our plan. First of all, we're going to take a look at log properties and 3 classic problems that are good examples of the types of reasoning that you as a calculus student need to be able to handle. And then, if we can, we'll do trig solving. Does that make sense to everybody? Okay. Let's go. The meat of what you need to know about logarithms are, first of all, logs are inverses or exponentials. So if we apply that idea to our exponentials, then we immediately have log base b of b to the x equals x, because my log function and my exponential function cancel, giving me x back. And likewise, b to the log base b of x is equal to x. And so these two statements are simply applying the definition of inverse in our particular case. Now immediately, this helps us with one of our classic problems, our first classic problem for today. Okay. So if I have something like this, ln of y minus 1 equals 2x minus 3. Little side note here, ln means log of what base?
Log of base 10.
Not log base 10, e, that's right. Log by itself is the common log of log base 10, and ln is the same as log base e. Log by itself is understood to be log base 10 in most contexts. Weirdly, when you get out into college math, log often means log base e, but not for our purposes. Okay? So, with this in mind, I look at this, I'm supposed to solve for y, and so I notice that y is found only in one place in my equation, and that's right there. I need to isolate it, so I need an inverse for this function. And the inverse, or natural log, is going to be e to the x. So I begin by raising e to both sides. And this is where I apply the inverse function to cancel out my log function. Having done that, these functions cancel and give me whatever was on the inside of that log. On this side, I just get 2x minus 3, e to the 2x minus 3. And now solving for the y is a matter of inverting again. Subtraction 1 is adding 1 to both sides. And we have our solution.
Yep. I thought there was more to that.
Nope, there's not more. When I say solve for y, I'm looking for y equals. So I have to isolate this guy. And once I get down to a natural log function here, then I'm going to cancel it by inverting. The basic spirit of all algebraic solving is you're using inverse operations. If you have 3x and you're trying to solve for x, you invert by dividing by 3. Does that make sense? Okay. So that's the first thing about logs. And then, because exponentials have 3 properties, so also logs have 3 properties. And so everybody needs to know the 3 log properties. The log of a product is the sum of logs. The log of a quotient is the difference of logs. And the log of a power is power times log. These 3 log properties you want to learn as forms, exactly as stated. Please do not memorize them as, when I see this, I do that. Please do not do that, because that way of thinking will keep you from being a good problem solver. Instead, you want to learn these as 3 properties that logs have. And if you learn them like this, then anytime you see the left-hand side in whatever form, then you can replace it with the right-hand side. Or, anytime you see the right-hand side in whatever form, you can replace it with the left-hand side. Whatever you need to do. Okay? And so that leads us to the second problem, classic problem that you need to be able to solve with logs. And that is, simplify this expression. The natural log of x squared over root x plus 1 minus the natural log of x. And so my goal here is, let me put parentheses around this so it's clear about what we're talking about. My goal here is to take this fairly complicated expression and to rewrite it in terms of things like log x, or maybe log of x plus 1, as simple as I can. Okay? And so the method is I'm going to take what I have here, and I'm going to compare that to my 1, 2, 3 log property forms, and see if I can see anything that is in one of these forms. Do you see any pieces of this expression that are in one of these 3 forms here?
Well, if you convert the ln's to log of e, then you could probably do log a divided by b.
Aha! Right here, log a divided by b. And actually, I can just write that as ln. There's no need to do anything converting. Yep.
Okay.
So, since this whole thing right here, what is the a and the b that you have in mind? What are the a and b that you have in mind?
ln x squared.
Yep. X squared is a,
ln squared root x.
is b. And so since this is in the form of log a over b, I can replace this with log of a minus log of b. Anything else I'm not going to touch. So, taking this expression right here, which is the ln of a over b, I simply replace that with ln of a minus ln of b, and the rest of it I leave alone, minus ln x. Well, already this looks simpler. I'm happy. Okay? Now, do you see anything else that's in one of my 3 forms here?
Oh, the log ab
A to the b.
in the ln x squared.
Aha! And so I could replace the ln of x squared with what?
2 ln x.
Exactly so. And now we get some payoff. Does anybody see anything that can be simplified here?
The 2 ln x and the ln x.
Yes, exactly. So when I combine those, I get
ln x minus ln root x plus 1.
exactly. Now, bonus question. Do you see anything here that is in one of my 3 forms?
Yeah, the log a divided by b. So, or, well, within the problem is log a minus log of b, and we can convert that to log a divided by b, right?
Yes. So one direction I could go is to convert this into this guy right here. This is one possible answer. This is simple in the sense that it's log of one thing. So I like this. So this is answer number one, and I have simplified it a little bit. Good. There is a second direction we could go also. Is a square root somehow related to one of my three forms here? What is another way to write the square root of x plus 1?
ln x plus 1 to the 1/2.
Mm-hmm. Yes. A square root is an exponent, specifically an exponent of 1/2. And if I now apply the log property to that,
Then it would probably be ln x divided by x plus 1/2.
careful.
Oh.
Oh, I see. You just went in this direction again. What if I applied the exponent property then?
1/2.
Yep. So what you said was correct. It was just equivalent to what we already had.
Oh,
So
yeah.
I just let that be. So we have a second possible way of simplifying it, and we would consider this also to be simple. It kind of depends on what we want to do with it, right? So I don't want you to think of one of these answers as right and the other as wrong, so much as I want you to think of them as two different simpler ways to write the equation. It is often the case when you're dealing with log properties that there will be possibly more than one way to go about it. For example, I could have, all the way back up here, I could have gone to this and said, oh, x squared is x times x. So I could write that as log x plus log x, which is the same as 2 log x's. So there's more than one way to get there with log properties often. Does this make sense to everybody? This is a kind of classic problem. Simplify this expression that you need to be able to do for yourself. Good. I'm seeing a lot of nods. I think you're good. Okay, good. All right. Now, the third problem relates to our idea of inverses. And here's the third problem. Find f inverse of x if f of x equals 100 over 1 plus 2 to the minus x. This one was in our homework. Do you remember this one?
Mm-hmm.
It was number 43, I think, on page 44. And many students struggled with getting the algebra right on this one. So let's take some time to do that. If I'm trying to find f inverse, then I am going to think about it like this. I am solving for x as a function of 1. So I need to first write y equals 100 plus 2 to the minus x, and my goal is to solve for x to find the inverse. Okay? Now, what's the appropriate way to do this? Well, I take a look at the situation, and the first thing that I notice that I really like is that there is only one place in my entire expression over here that x appears, and that one place is right here. So really, it's just a matter of finding out how to isolate x. I do notice that x is in the denominator of this expression right here, and so I would like to make it be in the numerator, and the basic strategy that we employ for that is what I call clearing the fractions. We're going to clear the fractions by multiplying both sides by the denominator. So here we employ a strategy or slogan, clear the fractions, and we do that by multiplying by the denominator, and that looks like this. I multiply both sides by y plus 2 to the negative x. And when I do, on the right-hand side, the denominator cancels with my factor. And on the left-hand side, I get this guy. Now, I'm trying to isolate x right here, so I have some options. One option, a good option, would be to divide both sides by y, since this is already in factored form. It's not the only possible option that I could have taken. So if we do this as kind of a choose your own adventure sort of thing, I could also distribute the y and get y plus y times 2 to the minus x equals 100. So this is another possible way of going about it. And I will develop both of these. Let's come back to the green branch over here and see how it works out. If I take this branch right here, it's fairly clear at this point that I want to subtract 1 from both sides. Like so. I can simplify this if I want to. I don't necessarily have to. And now I need an inverse for 2 to the minus x. What is the inverse of 2 to the splat?
Is it 1/2 x?
What is the inverse?
1 over 2x?
None of the above. What is the inverse of an exponential? It's a log. The inverse of the exponential is the log. So notice that inverting does not mean reciprocals. That's where your mind wanted to go. Inverting means finding the inverse function. And that inverse function is the log. So I take log base 2 of both sides. Like that. On the left-hand side, these two cancel, giving me the opposite of x. Like so. And I'm just about there. I need to solve for x by multiplying both sides by -1. And lo and behold, I have found my inverse, but I need to clean it up a little bit. The original problem told me to find an f inverse of x. If I go down and look at my answer here, what variable is given to me in this expression?
The y.
Y. This is f inverse of y, not f inverse of x. So if I wish to make it f inverse of x, then I have to use the variable x here. And so I would write my answer in the terms that they asked for by writing this as this. And the change of variable is only because the problem asked me to. Well, what if I had chosen the blue branch instead? Should I get the same answer or a different answer? Same, because the inverse function is unique. So, how do I solve for x here? You guys take over.
Subtract both sides by 1.
Uh-huh. Okay. Somebody take over for Saul. He's been carrying the team here. Keep going, and now we've hit the same point we did last time. I've got 2 to the negative x. I need to solve for x, so I need, what's our I word? An inverse, and the inverse of the exponential is the log, specifically log base 2. So, tell me how it goes. Orion.
Log base 2 to the 2 minus x equals log 2 100 minus y.
Okay. Brian, carry on from here.
The log base 2 and the 2 cancel themselves out. So it'd be negative x is equal to log base 2, parentheses 100 minus y over y.
So x is
Negative log base 2.
blah, blah, blah. Okay. Now you promised me that I should get the same answer, and when I compare the answer that I have here to the answer that I have here, they do not have the identical form. That doesn't mean I did it wrong, and it doesn't mean they aren't the same necessarily. I need to try to reconcile them.
Can you just like separate them? Like 100 over y minus y over y?
Aha. Let's see if we can justify that with algebra. What is a way to rewrite division? Division is the same as what? Multiplying by the reciprocal. That's right. So if I think of this as 100 minus y times 1 over y, am I allowed to distribute that 1 over y to each term? Is that a property that we have? The distributive property of multiplication. Yes, it is. And so I can do exactly what you suggested, Tom. I can write this as 100 over y minus y over y, which is the same as 1. Hey, look, now they match. We reconcile our two answers. And then, of course, in the blue version, we would represent f inverse of x as 100 over log, negative log 2 of 100 over x minus 1. This problem is an example of a detailed algebraic problem. And in order to do it and do it correctly, we had to patiently walk through the process of applying inverse operations to both sides. Look at how I did inverse operations every single time. In my first step right here, I did the inverse operation of dividing by 1 plus 2 to the minus x, and that was multiplying both sides by 1 plus 2 to the minus x. And the strategic goal was to clear the fractions, making my life easier. And then in the green version, I divided both sides by y as the inverse operation of multiplying by y. And then I did subtracting 1 as the inverse operation of adding 1. And then I did log base 2 as the inverse operation of the exponential. And then I did multiplying both sides by negative 1, or dividing both sides by negative 1 as the inverse operation of multiplying by negative 1. Ah, the log base is 2 because the exponential base is 2.
Wait, the exponential base is 4, that log base is 4, or?
Yes, and if you go back to the general log statement, the inverse of b to the x is log base b. And that's it. How are we doing? Good. Okay. This is all the log stuff that you need to know. In terms of material, the inverse property and our 1, 2, 3 log properties, the forms, are the stuff you need to know about logs. There's one more thing called change of base. We'll deal with that at another time. But, and then the 1, 2, 3 classic problems that we worked here are problems that you at home want to take and make sure that you can execute without error. Okay? Let me pause the recording for just a moment. Okay, we're back. So, since we have a little bit of time, the rest of my time I want to spend on solving trig equations. Christine? Yes, I can. The rest of the time I want to spend on solving trig equations. And I want to talk about two different tools that we have for solving trig equations. One of them is the unit circle. And I saw Ryan practicing yesterday his unit circle. Good job. And hopefully all of you have been practicing your unit circle so that when you have your quiz on Monday, On the unit circle, you'll be able to execute smoothly and cleanly. That's the goal.
What is the quiz gonna be about? Like, are you just gonna give us a blank unit circle, we fill it in, or do we have problems dealing with?
As I mentioned on Tuesday, the format is going to be, I'm going to ask you questions such as, what is sine of 7 pi over 6? And I will ask you such questions as, solve on 0 to 2 pi, tan x equals 1.
Okay. Yep.
So those two types of skills need to be augmented. So
Would
yeah,
there be like negative angle measurements?
could be.
So does it go all the way to like cotangent, like on?
Oh, yeah. All 6 trig functions are fair game.
We can take whole period.
No, you will have, you'll have 10 minutes for 10 problems.
10 minutes or 10? Oh.
Yeah. So the expectation is that you have it really automatic for yourself. That gives you, actually a minute's a long time. If I ask you what is sine of 7 pi over 6, very quickly you can go 7 pi over 6. So you can do, somebody who's experienced can do that in about 15 seconds.
Pastor will be like really simple.
They'll be really simple. It's just
Not
going
gonna
to
be
be,
like this, right?
no. Right. It's going to be very basic. Do you know your unit circle is the question I'm trying to ask. Yes. Okay, so let's talk solving. Solving trig equations. The first tool is our graphing calculator. And our second tool is going to be our unit circle. Obviously, you have done some work with both of these, so in some sense this is a review. But today I wanted to put it all together and ask this question. How do you know which tool to use? If I give you, for example, this equation, sine x equals 1/2 plus cosine x, or this equation, cosine x equals negative root 3 over 2, or this equation, tan x equals x, and all of these to be solved on the domain 0 to 2 pi. Then how can I assess whether I should use my calculator or seek to use the unit circle?
Is there like one way? Is there an answer for that?
If it's,
Or you
if
just
it's
do
like
it
the
real
angles
quick?
you know, like 30, 45, or 60.
Aha! So one thing you're looking for are, he called them the angles you know. What term did we give to them? Special angles, that's right. So if I see evidence of special angles in play, do you see evidence of special angles in play in any one of these?
The second one.
The second one is definitely a special angle. And since it is a special angle, I can use the unit circle to solve that equation.
So we're allowed to use our calculator for the quiz next week?
No.
Okay.
It's strictly a unit circle special angle quiz.
Oh, okay.
Yep. Okay. Okay. Are there any other, here's one thing you may not have thought of, but it's very true, and I want my students to be alert to this. One context clue that is extremely important is the directions. Problems that I give to you will often come, almost always come, with directions. You can use your graphing calculator, or you cannot use your graphing calculator. So look for the directions. and it was always written as you may not or you may use your graphing calculator here. If the directions allow you to use the graphing calculator, that's a really good idea. It may be the case that we're working along and you have these three questions right here and you see this question, you go, oh, I know that special angle, and you just do it from memory and that's okay. But even there, I would use the graphing calculator to check, because sometimes our memory is long. So the general principle is, if you see the magic words, you may use your graphing calculator, what that really means is you should use your graphing calculator. Does that make sense? So these two context clues, if you see a special angle, go ahead, unit circle. If you can use your graphing calculator, go ahead, use your graphing calculator. And hopefully, you won't see any questions that tell you you can't use and that you don't have special angles. I'll come back to that idea in just 1 second, because we're going to give a smart alecky answer if that happens. Okay? So, with that in mind, let's take a look at this third equation here, because I'm a little short on time. Let's look at that third equation there and see how we would use the calculator to solve on 0 to 2 pi. All right? You've done this before, so there it is. Get your calculators. And you know the drill. I'm going to let, how do I solve tan x equals x here? Put tan x in y1. And put 10.
What was it?
Tan x equals x.
Well, you put tan x in y1 and then just x and y.
Yes, that's right. So the slogan is y1 equals the left side, y2 equals the right side. And now I need to make sure that my window size is correct here. The domain of the problem is 0 to 2 pi, so my window size needs to also be 0 to 2 pi. Otherwise, I will find extraneous answers, or fail to find answers, that I need to find. So I'm going to hit 0 to 2 pi. Notice your calculator is a nice, lovely pi button right there, but then it converts it to a decimal. Looking at the graph right here, I can see that my y window size doesn't show me all the intersection points. So I'm going to expand my y window size to be negative 10 to 10 to see if I can capture all the intersection points that way. Huh, that's funny. Okay. Let's graph it and see what we get here. Here comes y equals tan x. And here comes y equals x. And now I can see, first of all, just look at it and tell me how many solutions we're talking about.
1. Well, 2.
Definitely 1. There. Oop, there. But what about over here? This is a little fuzzy, isn't it? It's a little
0.
hard to tell. Yeah. So we may have to expand right here to see if we're looking at what are the possibilities. They could intersect right at 0. It could be that this red line cuts through the curve twice. Or it could be that it misses it just barely. Right? So I'm going to need to expand it a little bit to see what's going on in just a minute. But first, let's find the solution point right here in green. So back to my calculator. We have second calc intercept. And we have our first curve, which is the tan x curve, and the second curve, which is the y equals x curve. And for our guess, I'm going to put my cursor close to the point in green and hit enter. And it's going to tell me that the intersection is at 4.4934. So I'm going to represent on my page tan x equals x, then x equals 4.4934. That's one solution. For the second, or maybe second and third solutions, I need to now change my window size so I can see this part of it more clearly. So let me change my window size to maybe 0 to 1 and 0 to 1. Oops. I did. There we go. And now let's graph it again and see what we can see. Here comes y equals tan x. Here comes y equals x. Oh, that's really close, isn't it? Yep. So maybe I'll do this. Maybe what I can do is second calc intersect. Watch how I'm going to be clever here. First curve and second curve. And for my guess, I'm going to put my guess out here with the understanding that the calculator is going to go this way and find the first intersection point here. And when I do, it thinks, oh, error, no sign change. It really did not like that. It must be that it's right on the boundary. So let's make my window size again be negative 1 to 1. And we'll do our second calc intersect thing. Sometimes you have to be patient with the calculator and think about what's happening. Error, no sign change doesn't necessarily mean no solution. It may mean that the solution is right on the boundary of your window. First curve, second curve, and for a guess, I'm going to try something like that. And now, there we go. Let's interpret this correctly. See how the x value is, what is this value?
1.3854 times 10 to the negative 6 power.
What does that times 10 to the negative 6 mean if I write it out in full decimal?
Well, if it were in full decimal form, it wouldn't be negative, but it would just be like a really, really small number.
It would. So, can somebody give that to me in decimal form? How many zeros? No. 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 No.
9.
No.
3.
5 zeros. Because watch carefully. 10 to the
Oh,
minus 6
yeah.
means move your decimal place to the left 6 times, so you get 5 zeros. So I can write this with 5 zeros, but since 4 decimal places is my standard, what am I really looking at here? What is this number really? 0. To 4 places. How come the calculator didn't tell me 0 exactly? Well, because the calculator in its solving can only do approximate solutions. And the solving technique that it uses is easily confused when the two curves get close to each other. It has trouble distinguishing between the one curve and the other, and it tends to see them as merging together a little bit. Now, that's not really how it happens. It's really using a method called Newton's method. But Newton's method is easily confused when the curve and a line that is tangent to it come close to each other. That's for the future, okay? So all of this is to say you have to be smart about what the calculator is telling you. And one of the ways in which you have to be smart is how to interpret error, no sign change. That means that it's not finding a solution in the interior. Maybe there's one right there on the boundary. Use the graph to help. And when you get a solution, please pay attention to the scientific notation here. And know how to interpret that. This means a really small number that is basically 0.
Oh, I have a question. What if it's like 1.384 e to the negative 1?
Then it would be 0.1385.
Okay. But which number do you determine that it equals 0 at like?
Because when I wrote it out in decimal form, it was 0 in all of my 4 decimal places. There you
Okay,
go.
that's what I thought too.
Yeah. If it comes out to 0 to 4 places, it's 0 as far as we're concerned.
So if it's 0.000184,
Then you would have 0.0002. Yeah, so if my calculator was telling me, this is for our listening audience here, 0.00018 here are my 4 places, then I'm going to write that answer as 0.0002. Are we better? Good, okay. Well, let's come back to the second equation, since we have a little bit of time, right there. And we'll solve cosine x equals negative root 3 over 2 on 0 to 2 pi. And the method of solution here, because I see a special angle, is to dial it up on my unit circle. And so I'm going to go to the angle such that the x-coordinate is negative root 3 over 2. And by the way, if the x-coordinate is negative root 3 over 2, then the y-coordinate would be either what or what?
1/2 and negative 1/2.
1/2 or negative 1. Right. It wouldn't be 1/2 and negative 1/2 at the same time.
Yeah.
It would be 1/2 or negative 1. Okay? And so then I would appeal to these 2 special angles, which I will have practiced on 5 pi over 6 and 7 pi over 6. And that's kind of it. Now for the hard question. If I use the graphing calculator, I'm good. If I happen to see a special angle value, I'm good. What if none of those apply? What if I can't use the graphing calculator and I don't have a special angle? Shoot. Let me do this real fast. Suppose I have to solve sine x equals 0.1 on the interval 0 to 2 pi. And I don't have a calculator available. Good news, bad news. Bad news, I'm not going to be able to get an exact value. Good news, I can be really smart alecky and simply say that one of my solutions is found with an inverse sign. See how I use those inverse functions there? But since I'm on the interval 0 to 2 pi, I expect 2 solutions. What is my other solution going to be? The inverse sine of 0.1 is some angle right there. The other solution has the same y-coordinate, and it is supplementary to it. So because it is supplementary, I can write it as pi minus the inverse sine of 0.1. So I can use my unit circle as a visualization tool to help me with this. These kinds of equations will not show up on the quiz on Monday, but I will talk about them in a little bit more information as well. Okay?
Will we go over last night's homework in a minute?
I'm not planning on it. If you do have questions about it, put them out on the note of, and we can discuss it.
We should hang on to it.
Sure, that'd be fine. You guys have a great weekend.
You too.